So, never walk under a ladder, but we can try to at least make sure that the ladder doesn't slide if anyone is foolish enough to walk under it. So let's have a look at this ladder problem. So the first thing I'm going to do, as with the majority of questions really, is to draw a diagram. The question doesn't give me a diagram, so I'm going to draw a diagram for myself. We've got a uniform ladder of length 3.5 meters and weight 150 newtons. That's a weight, so that's a force resting against a house at 76 degrees. So there's a little picture. The 76 degrees, the force of 150 newtons concentrated at the center of mass, which is 1.75 meters away from each of the ends. So we've got a window cleaner now who wants to stand with a bucket of water 3 meters from the bottom of the ladder. So 3 meters up the ladder, something like this. And we want to know what the force is. But the thing that I'm noticing here is we've got a mass and a force. We've got two different things to compare here. So if we want to find the force, which we do, we want to find the force which is going to be created by the window cleaner and the bucket. We need to multiply this mass by 9.8 by G before adding it to the force of 50 newtons from the bucket of water. So the force of the window cleaner and the water together is that. So that will be concentrated at this point 3 meters above the foot of the, or I think 3 meters from the foot of the ladder. So there's the distance of 3 meters and the force. So we're now told that the house is smooth. What does that mean? Well, it means that there won't be any friction at the contact point between the ladder and the house. There will, however, be a normal reaction that will be at right angles to the house. And the only other forces we need to consider are the forces at the foot of the ladder. We'll have a normal reaction from the ground, and we will have this force that we're trying to calculate, which will prevent the ladder from sliding. So that will be in that direction because the ladder wants to slide in this direction. So tidying up the diagram, we've got all of our forces now, and whenever we've got a situation like this, we can resolve vertically, we can resolve horizontally, and we can take moments. Those are the three things that we can do. And I'm going to do them in that order. So resolving vertically first, we've got 1, 2, 3 forces in the vertical direction. And when we resolve, we've got R2 minus 150 minus 863.4 equals 0. So the total of all of the forces equal to 0 because the ladder is in equilibrium. So the normal reaction at the foot of the ladder is 1013.4. We might not actually need that. If we take moments about the foot of the ladder, we might actually not end up needing R2, but there we go, we've got it anyway. When we resolve horizontally, we've got two horizontal forces, R1 and F. So R1 must equal F. The final thing I'm going to do then is to take moments about the foot of the ladder. The reason for that is that it eliminates two of the forces. These two forces have got no direction, no distance between the line of action of the force and the point we're taking moments from. So we've got to look at the moments of the 150, the 863.4 and R1. Now the 150 is the distance is this distance here. So that distance is 1.5 cos 76. So the moment of the 150 force about the foot of the ladder is the magnitude of the force multiplied by the distance of the line of between the line of action, perpendicular distance from the line of action to the point we're taking moments. The 863.4, the distance we're interested in here is this distance here, which is 3 cos 76. So that's why we're multiplying the 863.4 by 3 cos 76. And then R1, the line of action of R1 is this line, so we need to know that distance there. And that distance is 3.5 sine 76. So when we look at all of the moments, we've got 2 clockwise moments, and then we've got a negative here because this moment is anti-clockwise, and then when we add all of those together, we get 0 because the ladder is in equilibrium. So that tells us that R1 is 203 newtons, and because R1 is F needs to be at least 203 newtons to ensure the ladder doesn't slip. So there we are, that's the answer to the question. What about the modelling assumptions that we've used? Well, a bit like the seesaw problem, we model the ladder as a rod, so it doesn't bend and it's got no width that we need to worry about. And the window cleaner and the bucket are point masses, so that they are concentrated at the point that they are touching the rod. So there we are, that's that question.